Well, this is where we were last time. We finished talking about expand capacity, which was just our way of tricking the thing into thinking it could expand the capacity of the array arbitrarily, but you can't really. And the array's never growing. It's just the contact list is growing automatically. And imagine that you're the person using the contact list. Imagine you're using a contact list class, but you didn't write it. You would never need to think about arrays, would you? You add things to it. I didn't need to think about an array. I just said add, and it did. If it ran out of room, I didn't care. It didn't matter. The class took care of that itself. Were there any questions about the add or expand capacity? Okay, so we got add, we got expand capacity. Well, now let's do like a contains and a find. Well, first, really what I want is a contains. And I want to get. I want to write a function, or pardon me, a method, where I can get a specific friend, maybe at a specific index. I want to check if a given friend exists. And there's a lot of things that I might need where I need to know where a specific friend is within the contact list. Like contains, for example. Although contains, actually, I really don't care if it's where it is. Contains just wants to tell me if a given friend exists in the contact list or not. So what I'll do is I'm going to write a private helper method called find. And it's just going to be a linear search. Because this linear search, this find method, is going to be used in several other methods. So instead of reproducing functionality in the various methods that need it, just write the method once and call the method. It's just like any other function that we do. Okay? So I'm going to write a private find method. And let's start by looking at that. I'll just copy it over and then we'll talk about it in here. Contact list. Oh, this is the actual class one. I don't want that. So here we go. Oh, we got to import objects. If you ever try to use object and it's red, you just need to import it. There, I just said import, and it added it for me. So here's find. Do a linear search. Start with a for loop starting at index 0. Go to the size. Because remember, size and the array's length have two different meanings, right? The array's length is the capacity, like how many seats are available. But size is the actual number of friends actually in the contact list. So I might have 1,000 seats available. I might have an array of size 1,000, but maybe only 10 friends. I don't need to iterate over the 1,000 things. I'll just iterate to 10, right? No need to keep going. So that's why I'm only iterating to size, not the friends list or contact list or whatever I called it, friends, I think. Not friends.length. And again, I'm calling the method size because whatever. And then I say, okay, if objects.equals friend is friend at index I, so this, by the way, mind the fact that this private method takes a friend to search for. If those friends are considered equal, return the index, return I. If not, keep going. And if I ever get to the end, we return -1, which of course has the label not found because we gave the static constant not found. We called it negative, we signed it -1. So that's that. That's your run-of-the-mill basic linear search. You'll notice I'm using the static objects here. That's good because someone might pass null by accident and that would then crash the program. So this is null safe, so that's good. But it's just the loop, and then if we ever get to the end, return -1. And -1 is, of course, what we call the sentinel value. It's a value that has special meaning in the context of how it's used. If we ever return a negative index, that obviously the thing doesn't exist at a negative index. It means something special. Cool? So now contains is going to be pretty simple. All I actually have to do is the contains method will delegate to find. So contains just calls find. And if find returns anything that's not found, it's there, right? So if calling find on that friend returns anything that's not equal to not found, it returns true, meaning that that object exists, that friend exists in the contact list. Questions about that? You might be noticing, and I mentioned this last time and I'll say it again, each of these individual methods aren't too crazy. They're not trivial, but they are simple, and that's by design. We could write this class in a way that's a lot more complex and it'll have the same functionality. But this is because while designing this class, we were cognizant of the design such that it's a nice simple implementation. Simple doesn't mean trivial, so I'm not saying that you should immediately understand this is easy peasy. No, that's not what I'm saying. But I'm saying, like, look at that contains. There's not a lot going on. Yeah?
Is not equals to not found?
It is not equal. This exclamation point, that means not equals. That's how you do not equals in Java, yeah. Okay, anything else there? So index of, here's one. I'm going to write a public method called index of. That will just call find and return the index of a given friend. So it's basically find, but instead of returning a sentinel value when the element's not found, it returns, well, what does it do? Well, it throws an exception. It throws a special exception called a no such element exception. And by the way, when you create an exception, in the parameter, or the argument that I give that exception there, I'm saying like objects.toString. I'm calling toString. It's a null safe version. So if that exception ever gets like thrown and is displayed, it tells you what the friend that wasn't there. I'll show you an example in a moment. But this is effectively find, but instead of throwing a -1 at you, it raises an exception. It throws an exception if it's not found. And this is the public-facing one. This is one that someone would actually call directly. Yeah?
Would it technically be kind of inefficient that it's doing a linear search there twice?
I see what you're saying.
Because like, couldn't you like have just
like if it returns -1?
Yeah, just have a variable that is like find friend, and then if it's -1, throw the exception, otherwise return.
So your point is we're doing a linear search here twice technically. This effectively calls find twice, right? You're absolutely right, but I'm really not concerned about efficiency for linear time things on this size. So yeah, it could arguably be optimized. In fact, I don't even know, maybe the JRE maybe Java would take care of this. I don't know. That might be a little ambitious, maybe not. But to me, this code's a little more clear the way it's written here. It checks like, okay, contains. Contains, I know what that means. It's got a very good name. It's a method that tells me if that thing exists. If it doesn't exist, raise that exception. Otherwise, just return the result of calling find. So this is an example of something that I think is a little clearer than doing what you were suggesting. But doing what you were suggesting would be functionally, it would function correctly. It would absolutely be correct, and it would eliminate a potential double linear search. So you're not wrong about that, but this is very readable, I'd say. Other questions about this one? Now, if you're saying, why raise an exception? Why not still like return -1? And that's a good question, and this really is just coming down to design. -1, an exception's perhaps a little bit clearer in this situation. We could get down to some like design philosophies of code. And one of them is if I'm expecting an int and I get an int back, I'm expecting that int to be an index, right? But if it's -1, oh, that's kind of like the exceptional thing. Well, we actually have something for exceptional things. They're called exceptions. So for a public-facing method, I would say the exception makes a lot of sense here. But in terms of actual design of software, it's not really bad to just have it return -1 in that situation. This is just a design decision. Let me show you an example of calling. All right, so here we go. If I say context dot contains or index of, let's say index of let's do another one. Let's do this one. So it's not boring and 0. There. We should see 0, 1, 2, 3. Building. And then what I'll do, yeah, so there we go. And now if I try to find a friend that doesn't exist, like this with a Z, we'll get an exception. We'll see that no such element exception, but it includes some useful information to me. Because in the contact list, the exception says, give me the string version of the friend you were looking for. So based on the toString written in the friend class, when we go back here, we see, well, this is the string representation of the friend we were looking for. So it's basically saying, this friend you were looking for, this one, the one that just printed out there in the exception, it wasn't found. It's more helpful than, I don't need to put a message in here. But if I go back and hit run, we won't see the friend printed out. And I just find it less helpful. It's better to have more helpful exception messages than less helpful exception messages. And this is fairly typical. Your exception messages, if you're searching for something or if you're calling and it's not there, you just print out the thing you were looking for that wasn't there. Or that's the message, not print out, that's the message you pass to the exception. Questions, questions, questions? All right, we're motoring along. All right, get. Okay, perfect. Look at this one. Get, you specify, it returns a friend. You specify an index, and then you just return the friend at the specified index. This is effectively an accessor for specific indices in the contact list, in the array. But you'll notice it's got a check on it. It's if the index provided is less than 0, index out of bounds exception, right? There's no such thing as a negative index. And if the index you're looking for is greater than or, does that make sense? Should it be greater than or equal to size?
Yeah, size is the next spot, the empty spot.
But it's empty.
Yeah.
You're right, yes, you're right. My brain's not firing and it's not even after, well, it is afternoon, I guess. So if they specify something that's too small or too big, raise an exception. What exception makes sense? Index out of bounds, right? Index out of bounds exception, that makes a lot of sense. Index out of bounds and no such element exception, these are built-in exceptions that Java has. Java has a lot, just like Python. There's a lot of built-in exceptions that kind of cover most of your cases. You can define your own exceptions if you want for very specialized cases, but you typically don't. You use what Java gives you because they're pretty standard. So you always just look to pick the type of the exception, what makes sense to throw in this situation. Here it makes sense to throw index out of bounds exception. But notice, it's checking based on the size, which is the number of friends in the contact list, not the capacity of the array. So that's interesting, but that's what we want, because if there's 10 seats but only 5 friends sitting down, I don't want to start accessing null, like empty seats, to return nothing from this method. Right? So just be aware of the difference between size and the length of that array. Other questions? Anything else? Everybody good? I'll give you a second to think. I feel like I'm expecting more questions. You're freaking me out. Am I this good that everything makes perfect sense so far? All right, I'll keep going. Remove. So this one gets a little complex, and we have a couple of choices here. And it all comes down to how do we actually want this collection to function? When I remove a friend, okay, let's talk about this implementation and talk about the implications of this implementation. So, first and foremost, if the friend is not in that collection, return false. By the way, this right here, in add and remove, returning a Boolean, is a very common pattern for a general purpose Java collection. We'll learn about interfaces soon, and we'll talk about maybe even the collections interface. Not overly important right now, but an add and remove typically returns a Boolean for a general purpose collection. When we hit stacks and queues and whatnot, they act a little differently, but we'll get there when we get there. And the Boolean is used to indicate success or failure on the add and remove. Now on the add, there is no such thing as a failure on an add. So it always returns true. But a remove, well, what happens if you try to remove something that's not there? What should we do? Not remove nothing. And so we basically do nothing but return false to signify like, well, the remove was unsuccessful. We could raise an exception here. We could. That wouldn't be wrong, but this makes more sense, and this, to me, and this is more aligned with your typical Java standard library. How most collections in the Java standard library are going to work like this. But it wouldn't be incorrect to have an exception here.
It seems like the end result is the same, because like the end result is you want a collection without that element in it. So if it's not already there, then
yeah, you just remove this thing. It wasn't there. Okay, great. Carry on. It doesn't matter to me, yeah. So if it's not there, just return false, you're done. So if it's not there, meaning it's there, what do? Well, we find the index of the thing we want to remove with the find method. I then say, okay, go to the friends array at size -1. What's at size -1? The last friend, because remember, size always corresponds to the next available spot because of zero-based indexing. So size -1 is, well, what's before the next empty spot? The last full spot, right? It's like with the three of you, I'm going to find, let's say with this row, right? There we go. Okay, great. There's 1, 2, 3, 4, 5, 6 people there. Your index 0, 1, 2, 3, 4, 5. Index 6 is where your bag is. Pretend the bag's not a human. All right? So index 6, which is size, is the next available spot. Size -1, well, that's you, the last person in the row. So I say the reference variable, which is the array at that index, to that human, to that friend, at that last one, go to the friends that remove index and put in it the last thing. So that's kind of like taking you, let's say I told you to leave. You don't have to get up. But let's say I told you to leave. Now I've got an empty seat. I don't want to leave a hole in my collection. I want it to be contiguous, right? I don't want to have a gap in my array. That's terrible. So what do? Well, here's what I'm going to do. I'm going to take the last person and basically put you there. Fill the gap. Then, now this next step isn't entirely necessary, but I'll do it anyway. I say friends at index size -1, so that old seat, set it to null. Then decrease size, return true. Now there's a couple of things to talk about here. First, I'm going to try to draw to visualize what we've done. Now in that example I just did there with the people sitting in a row, it wasn't, remember that I was talking about, oh, the people are sitting in the seats are the array indices. But really, there's no friend object in those array indices. Its references to friends are in those array indices. So, perfect. Let's say we remove this person. Right? I know, I'm seeing people go, I know, it's nice and bright. So I've got a gap. So what am I going to do? Well, all I'm going to do is say, there. All right? That's what I've done. That's what happens on this line of code. In fact, let's do this again. Really, did I ever say, hey, remove index equals null? Did I ever actually really clear out remove index to nothing? No. The thing at remove index? No. Really what I did was this friend, I'm just going to move them temporarily for the sake of demonstrating. There. And now, presumably nothing references what was there before. And remember what I said last time, or maybe it was the time before, what happens when you have some object in memory that's not referenced by anything? Garbage collection comes along. If you can never get access to that thing anymore, it's just wasting space in the computer. So there's this process in Java that comes along and goes, well, okay, you can be removed. So they disappear. So that's what happened on this line. Okay? Now, let's skip this one for a second and talk about the implications here. We reduce size. So now, size is 1, 2, 3, 4. Okay? Size is 4. But you'll notice index 0, 1, 2 and 4 are aliases for one another. And this is a bit of a recipe for disaster. But it doesn't really matter in this particular case because size is 4. I could never actually index the thing at index 4 because that's outside of bounds. If I tried to say, get the thing at index 4, that would raise or throw the array index out of bounds, or index out of bounds exception, right? Even though there's something kind of there, but it's not really supposed to be there. Further, if I go and add a new friend, if I called add immediately after this, where would that friend go? Index 4. What size is index 4? Meaning that this alias or this reference would get updated to the new friend wherever it is. Oop. Right? And it wouldn't really matter. But I'm adding this line here. Functionally, it's really not that important, but to me, if that data isn't really there anymore, it's not really supposed to be there anymore, get rid of it. It makes a little bit more sense to me. Just clear it out if it's not really supposed to be there. If you're like, well, it's not there, sure it's there, but no one on the public-facing side would ever notice that it's there. Yeah, but by setting it to null, we know it's gone. If it's not there, make it not there. If you didn't include that line, I wouldn't care. But I think that this is clearer code. It makes more sense with the spirit of what the goals of this method are. And you're probably getting a sense of, like, programming, there's a lot of gray area. There's a lot of qualitative thinking that you need to have here. It's not just quantitative stuff. It's not right or wrong. There's a lot of black and white, and there's a lot of gray in between. It's a design decision, not important, but there we go. Any questions about that strategy? Yes?
Would you ever want to move each element down?
So, that's exactly what thank you for asking. So what would that mean? Well, with the code as it is, if I have an array, I have a friends list of 1 million elements. I have 1 million friends in my friends list, and I want to remove the thing at index 0. How much work is being done in this method? A fixed amount. I say, okay, index 0, you reference the thing actually at size -1. Clear it out, decrease size. But if I were to move everyone down 1, I have to move all 1 million friends down a spot. Or 1 million minus 1, because 1 was removed. But I got a lot of shuffling to do. So this right here is constant time. Meaning, no matter how many friends are in there, this is going to take the same amount of work. But by shuffling everyone down 1, the bigger the array, the longer that would take. Sorry, the more friends in your collection, the longer it would take to shuffle everyone down 1. But it all comes down to how do we want this collection to operate? For our purposes, this collection, the order does not matter. The order of the elements in this collection don't matter at all to me. I don't care who comes before what. It really doesn't matter. There are a lot of times where the order of the elements in your collection really matter. And if the order matters, you gotta shuffle everything down to preserve the order. If you start taking something from the end and throwing it somewhere in the middle, that's gonna break everything. So because order doesn't really matter to me, we can have a constant time remove. If order mattered, I'm gonna have to have a linear time remove in this particular situation. Yeah, so fantastic question. I'm pretty sure on the assignment I'd say order matters. Do I? Yeah? So I say shuffle everything down, yeah? Okay. Cool. Other questions? That was a great question. That's good. Your head was in the right spot to think that. But it's always like a give and take, right? If you think back to like binary search, a regular linear search is linear time. But if we know that the data is sorted, we can actually have logarithmic time search, which is way better than linear time. It's all a consequence of the state of the data and what algorithms work and make sense for that data. It's always a give and take. No silver bullet. Questions, questions, questions? All right. Oh, look at that. I already had an image. Cool. Clear. All right. Well, the easiest way to do a clear, if I ever want to just obliterate all my friends, this is the easiest thing to do. Set the friends array, just be a new array. And then what's the size? Well, it's 0. There's no one in it anymore. And then if you say, well, what happens to the old one? Well, if nothing's referencing that friends array, the old friends array, garbage collection comes along and gets rid of it. It's kind of like expand capacity without copying things over. It's just create a new array. Yeah.
So you could do the same thing like in remove, where you don't have to make a new array. You could just set it to 0, size to 0.
Remove?
Well, like in the remove thing, you set the last element
to null. Yeah.
But could you also just set the size to 0? I mean, I guess you would also maintain it.
Yeah. Oh, I see what you're saying. Yes. Yes. We could leave it alone and just set the size to 0. They'd all still be there.
The length of the array would stay really big.
Yeah. So now, but though you'll notice the way I implemented this is I made this array the same size as the previous array, whatever it was beforehand. Maybe I should have made it default capacity, whatever. That's not that important. But yeah. So to clarify, his question was, well, could you have left the array alone and just said the size was 0 and leave the array unchanged? And absolutely we could have, but then we have that situation of like, but it is full of references to friends that by setting size to 0, no one would know they're there, but we know they're there. And they really shouldn't be there, so just clear them out. Doesn't really matter, but kind of does, but it doesn't. Yeah. Clear. What else we got? ToString. Now, okay, so let's talk about this first. So, whenever we have a nice, simple, straightforward collection, object, like a very simple Java object, if we don't have anything in mind for what we want the ToString to look like, we always follow that pattern of like name of the class, open parenthesis, fields, close parenthesis. All right? Like we saw with the friend. For a collection, they're all probably going to look very similar in that you've just got some linear collection, assuming it's a linear collection, a linear amount of data. For our purposes, what I'm going to do is create the string version of the friend, add a new line, and then have each subsequent friend on a new line below it. All right? That's how I'm going to do it. And if you say, why? My answer is, because I want to do it that way. I think it makes sense. If you're like, no, I want them to be all in one line, fine, you can do that too. But I'm just going to have each friend that's in the collection be represented on its own line in the string for the collection, the contact list ToString. And how am I going to do it? Well, I'm going to loop over for the size. Remember size, not the array's length, because that's the capacity of the array, not the actual number of friends in there. Loop over each one, get the string representation of the friend at index I, add a new line to it, repeat, 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 repeat. But you'll notice we're using something called a string builder. And we're not really working with strings directly. And this is because strings are immutable. Remember in Python how we always did like plus equals with the strings? Remember that? If we kept wanting to append to a string. But at the end of the day, we couldn't really actually append to a string. Every time you did that, you needed to make a new string. So that's actually like really resource intensive, especially if these collections get big. So if we keep making a new string, every time we like append to the end of the string, it actually creates a new string. And if we're doing that a million times, poor computer. So what we do instead is we use this tool called the string builder that basically keeps track of all of the individual strings we want. And then when we're done, it returns one actual string in the end. So this is just a nicer way to do string building. Java has a built-in tool. So I create a string builder object. I start with it being empty. Think of it as an empty string. I append to it the friend at index I. I append a new line, repeat, 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 repeat. And when I'm done, if I did this, it would be unhappy because this function or this method would be returning a string builder. So we actually need to tell the string builder, okay, now give me the string. Call toString. So this returns the actual final string. So string builder just makes building strings so much easier than how we were doing it in Python. Although it would be very similar. It's just easier and nicer on the computer. So there's our toString. You'll notice here I didn't need to call toString. I could, doesn't really matter. It'll automatically get called in this context. If I go here, now if I run it, what do we see? There. Our friends. A, B, C, D, E, F. Cool. Any questions about what we're seeing here? I'm shocked at how quiet it is. You're freaking me out. Are you really all like, yeah, I get it. Come on, move on. Raise your hand if you're like, yeah, I'm fine. Ah, see? Half of you didn't. So where's the issue? Help me out here. I can't read your mind. All right. Okay, I'm going to have a quiz. I'm going to test you right now. Here's my test. I'm not going to hit run yet. What do you expect to get printed out? Don't say it out loud. I'll give you 10, 15 seconds. All I did is I added this remove here. What exactly will get printed out when I hit run this next time? All right? That's what I'm asking. Okay? I'll give you a few seconds. Look at that code. Raise your hand if you were right. A, B, F, D, E. Why? Well, we got rid of C and F got replaced basically at that index. So there we go. Yeah?
In the remove thing, do you have to have new?
No, this is because I was being lazy and I just created it. I would because on this line of code, I'm doing two things. I'm creating a new friend object, and whenever we create a new object, we need the new keyword. And then I'm calling remove on that new one. If I signed each of these their own like reference variable, I wouldn't have needed to, but yeah. I don't know, I don't like having one line of code do multiple things, but here I am. All right. Now equals in hash code. All right, so this one is kind of tricky. Because it's really not the best equals that I could write. In fact, I would argue that this is kind of a lame equals. But first I say, okay, are sameness, or if they're literally the same thing, return true. If O's null or their classes don't match, return false. Cast it as a contact list. And then there's actually a static method that will allow me to check if arrays are equal. But what's neat is the arrays actually don't need to be the same length. I specify which indices in the arrays I care about to check. Okay? So basically, in this array from index 0 to the size, in that array from index 0 to that one size, check it, right? So one might have 100 spots and one might have 5 spots, but if it's only 5 friends I care about, they're only going to compare the 5 friends. Now, can anyone take a wild guess what I don't particularly like about this equals? It cares about the order all of a sudden, even though a moment ago I was just saying I don't really care about the order. So I was saying with this collection, I really don't care about the order of the elements. But if I checked 2 friends lists, 2 contact lists, where they had the exact same friends in them, but they were in a different order, this would say they're not equal. And maybe that's fine. I would say, really, if I were writing this, if I were rewriting this, I would probably check it where I would specify that I don't really care about the order when writing this. I would write this in such a way where order doesn't matter. But that's kind of hard to do. And we're at the very start of 162, so we're not going to do that. But as an FYI, realistically, this could be improved. And then here's the hash code. There's quite a bit going on in here. First, I hash the size, and then I loop over each element in the array. And every time I do that, I multiply. It's weird, and I'll explain why very high level, and I'm not going to go into more details because it's well outside the scope of this course. I'm always adding to. What I want to do is I want to take the hash code of each element in the array and add them together. But there's some issues with that. And without getting too much into details, every time I do that, I take the current running total and I multiply it by a prime number, specifically 97. Why? Because it's magic. All right? It magically makes it far less likely to have hash collisions. It makes it far less likely for 2 unequal things to be mapped to the same integer. And that's what we want to avoid with hash codes. So that's what we do. And if you're like, what? That's all you need to know. That's really the extent of it. So next time you're writing a hash code for a collection, just reference a hash code for one of the collections we've already written and just do it yourself based on what this looks like. Because think for a second. I was saying order mattered. But if I just added up the hash codes of all the elements, that would suggest that order didn't matter, right? Because 5 plus 1 and 1 plus 5 are the same, right? So we do this thing with the prime numbers to make them way different. It's magic, all right? Questions, questions, questions? Cool. Most of our equals for plain old objects, like our friends, our countries, our courses, are all very similar. Our equals for our collections, like our contact lists, our country catalog, our course list, are going to be fairly similar. Those are the 2 main templates we're going to follow for our equals and our hash codes. There's the simple ones and then the collection ones, and they're all going to be very similar amongst themselves, amongst their groupings. Yeah?
Why is hash code final?
Why is it final? It doesn't have to be. I just made it that way. Don't worry about it. I'm actually surprised I didn't make other things final, but don't worry about it. Good observation, though. All right, hash code, warning. Okay, yeah, cool. Questions, 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 questions. Nothing. So, now we can actually start 162. Everything up until this point was effectively review, whether you like it or not. It was. It was review of 161's content, but Java, right? So now we can actually start 161's content. And like I was saying from the beginning, the majority of 162's content. 162. The majority of this course, its explicit learning objectives are along data structures and their algorithms that go with those data structures. The implicit learning objectives are like, okay, you become a better programmer, you learn some more Java and whatnot, just because we're using these tools as we go. But the big focus is data structures, collections, ADTs, abstract data types. Right? So a collection really is just a group of something. A course list, a country catalog, a contact list, right? It's just some collection of things. And in computer science, we have a few very popular elementary collections. Stacks, queues, bags, lists, trees, graphs. And the ones we're going to talk about in this class are going to be stacks, queues, bags, and trees. Trees are nonlinear collections. Stacks and queues and bags are linear collections. Linear meaning that you can kind of start at one end and go to the end, just one at a time. A tree, linear collection, stacks, queues, yeah. A tree, if I say you're at the root directory and I say what comes next, you go, well, what do you mean? It depends, right? If we're here in the queue and I say what comes next, there's no questions asked, it's that one. Why? Because it's the next one. Trees. And then there's graphs. We're not going to touch these, but graphs are a generalization of trees. We use graphs to represent relationships between things. The things in this example are like airports, and the relationships are connecting flights between these airports, just as an example. But you can use graphs to represent whatever the hell you want. And we'll stop here. All right, I'll see you all later. And be aware the assignment is due Monday, so don't forget that.